Good evening, everybody. It's a nice day today in New York City, even we're still under the pandemic of the COVID-19. The weather is nice evening. I'm sorry to have this event at 6 o'clock that you don't have to, you cannot go out to enjoy it, but you can always see the recording later on. My name is Dennis Poon. I joined Thornton Tomasetti Engineers in 1977, and since now I work with Thornton Tomasetti for 43 years. It has been a great honor working with Thornton Tomasetti, and we gained a lot of different experience. And Thornton Tomasetti is fortunate enough to win the engagement to be structural engineer of many landmark buildings. And if you go to the CDBUH resources, you can see all the tallest 20 building in 2020. The one underneath there has been worked on by Thornton Tomasetti. So we have a good mix of different high-rise buildings to share our experience and make it more efficient. And one thing I want to point out to everybody, how do we design a super tall and mega tall? So according to common practice and CWH guidelines, we define super tall for buildings over 300 meter tall and mega tall building over 600 meter tall. So now with all the high-rise buildings going around the whole world, they're very expensive to build, and they have to resist wind load, lateral forces, gravity load. So the efficiency of the design is very important. One of the efficiency design comes hand in hand between architecture, the forms, and the efficient structural system selection and engineering and details. We finished the Kingdom Tower design, which is under construction, and it's a height of 100,000 meters. So the architectural form is a table shape. It really helps us to reduce the wind load and also lower the center of gravity. And Shanghai Tower, there's another great architectural forms that makes structure design more efficient and lower the cost. And we have a twisting shape, we have a table shape. And we also reduce the wind load and the vortex shedding effect with the special architectural forms. For high-rise building or any upright structure, when wind is blowing towards the building, people think that that will be the wind that will be created. That's not true. When wind have to bounce, goes through the tower on each side, you will create the vortexes. And these vortices is causing negative and positive pressure on the crosswind side. And since they have the positive and negative effect as the wind is blowing alternately on each side, it will cause a crosswind, and this crosswind can sometimes be higher than the direct winds on the building that cause the building to fluctuate more. And this is an extremely important aspect when we study the wind effect on high-rise building, is how do we minimize vortex shedding effect. There are many ways we work with the architects and the wind tunnel consultant how to maximize on the tower shape and its impact on the aerodynamic performance. And we have a lot of shaping strategies. And after we find out the shaping strategy that works with the functionality of the architectural design and the structural design, we can proceed with the efficient structural design to go hand in hand. So this is the Pingan Tower, and we end up creating the notch corner that create more corner office, at the same time create architectural effect that make it more beautiful, give a distinct shape to the building, and also create a aerodynamic enhanced performance to the building. Other buildings, you have recessed holes. On the building on the top, on the right-hand side is the Wuhan Greenland, we created slaughter hole. And the one in the middle is the building in Incheon Tower that was not built, but was designed to a certain extent. And we have slaughter hole for as part of shaping strategy. The Taipei 101 is another great example on the left, which I can talk about it. So we have a lot of shaping strategies that goes with structural engineering and wind tunnel testing and architecture design to provide an aerodynamic. Even today, even you ride a bicycle and the bicycle head, you have to worry about aerodynamic effect, which is important for high-rise, any high-rise wind design. But even for high-rise building, the high-rise building have a certain slenderness, which is the width, the ratio of the height of the building divided by the width of the building is the slenderness ratio. When the building is too slender, it will be too flexible. So, and also the tower core itself may not be enough to resist the lateral loading or for the bending of the tower or the stability of the tower. So normally we try to, just like a skier, when the people is skiing, they are holding on each hand a ski post. And in the building, we don't hold a ski post. We extend out from the tower core, the main body of the building, extend outward with an outrigger truss, outrigger system, and connected to the column. We call it the outrigger system. That is greatly improve the building stability with this outrigger system. It is a very important tool for structural engineers to design high-rise buildings. Petronas Tower. This is a very important landmark building. The reason I say important for that, for a landmark, because we all remember that the World Trade Center Twin Tower was finished around 1972 and 73 for Tower 1 and 2. And after the completion of the World Trade Center Tower, the world tallest building, there has not been many or any high-rise or super high-rise tower over 100-story being built until Petronas Tower comes in around 1998 completion. So for almost 25 years, the world has not been very active or busy with super high-rise towers. And Petronas Tower is the first one, starting the design around 1995 or 92 in that period of time by our office. And Thornton Tomasetti was working with Cesar Pelli office as a structural engineer on this landmark building. This is at that time the world's tallest building, but it is in Southeast Asia. And in Southeast Asia, the construction skill, the availability of the of material are totally different from America or the Western world. So the design challenge is that we have to find what is the locally available material and the local skilled labor. And also we have to deal with the foundation issue because in many Asian countries, they are found in near the river area with soft soil, and they don't have that kind of great bedrock profile. And also for Petronas Tower, we also have a challenge is the sky bridge. So how we solve the problem is basically Malaysia is with a lower cost labor with concrete construction. So we try to use a lot of concrete material and also use steel material only where it's needed for the speed of construction. So basically we end up using a mix of steel and concrete construction where it is needed. For the foundation issues, we want to make sure that we have a good foundation so the tower will not tilt. And in the Petronas Tower case, because the soil depth between the bedrock and the top of the surface it varies due to the underlying bedrock condition. So we end up have to do a lot of analysis to adjust the height, the depth of the pile so that they have the same settlement and elastic shortening. So we end up using the barrier piles with different sizes, connecting with a mat foundation. So we have a thick tower mat for the main tower and the bustle. I want to make sure that this Petronas Tower chief structural engineer and the lead engineer is my colleague, Len Joseph. And I'm working with him and the TT team on this job. So basically it is Mr. Len Joseph leading the team on this great project. With us start learning a lot about high-rise, super high-rise building. And we learned a lot. Now with this typical floor system, we end up using a reinforced concrete core, steel rebar reinforcing core, concrete columns, and also concrete perimeter haunch beams in order to make full use of the local available labor and concrete material and bring the cost down. For the speed of construction, we use a typical wide flange floor beams, and then with a concrete slab on metal deck, which is quite easily available in Malaysia. So we have to look at the local situation in order to select our material and the construction and the structural system. So this is the concrete perimeter beam around on each floor, which this core with the perimeter beam is working as a moment frame. Is together as a lateral system to resist wind load and horizontal load and the stability for the building. What is a moment frame? What is a perimeter frame? A frame is a semi-rigid structural structure with on two columns with a rigid joint at each end, with a rigid connection at each end of the beam, and you can see the rigid joint of the beam. So this is the concrete construction, and you can see now this is a very high-rise building. The building will move, will deflect at a different shape due to wind, but we have a connecting bridge. So we do not want the bridge to become a tying link between two strong towers. So we designed the Mr. Len Joseph designed the bridge, and is to be able to move between the two super tower with the center leg supporting it with all kinds of joints. You can see at the leg there's a ball joint that allows the legs to move, and so on. So but the leg is so long it will vibrate due to wind. So we have a spring activated pendulum underneath the bridge. Now, after the completion of Taipei 101 in 1998, we already start working on Petronas Tower. After completion of Petronas Tower, we already start working. Myself and my team start working on the Taipei 101, which is located in Taiwan, Taipei, the capital, and they also break the record again to be the world tallest building at that time, with a 508-meter tall. But the challenge is even greater than Petronas Tower, because Taiwan is located at a very high seismic zone, an active seismic zone, and also have yearly high typhoon or hurricane window, but we call it typhoon window that we have to deal with. And also has a very not so ideal soil condition. So the seismic factor for high-rise building get us into a different category of design. So how do we design it? And also we also have to take care of the vortex shedding and building acceleration, because we cannot make the building too stiff. It will waste a lot of material to reduce acceleration. So that's another phenomenon we have to discuss. So we also end up putting, but in Taiwan, in that area, because it is a very severe earthquake zone, and steel is quite available, import steel is quite available, and they have a skilled steel labor. So it becomes an all steel building. But we are also using a super column idea, and a super column idea to create a mega frame, and create a mega frame around the perimeter. The blue is a mega frame around the working with the super column as a dual system, okay, and working with the outrigger system in each direction for greater stability. So you can see the lateral system for this super high rise again is basically a core with outrigger on each side, and then the outside transferring to load to the super column, and also with in this case every 8 floors, we have a belt truss to form a girder is called a mega frame. And so you can see how this mecha frame works. You see, this is the mecha frame and the outrigger system and the super column, and this is the bell truss as a exterior mecha frame. And the reason why we use super column is that when the building want to tilt, when you put all the weight on these two super columns, the dead load will balance the uplift. That's why the super column ideas comes in. This is a steel column that we infill it in concrete. We have to make sure that all the concrete are properly infilled into this steel box column. As myself and my colleague are visiting the site. The building is very tall. It will easily, because of high wind, you will have acceleration issues. So we end up to have a famous pendulum, a wind damper that will move against the swinging of the tower in order to slow down the building acceleration. So occupants or the tenants of the building will not get motion sickness. Shanghai Tower, after the, since the early 2000, there has been a lot of super high-rise and mega high-rise building projects springing up all across China. And another one, Thornton Tomasetti and myself work on is, and my team working on is the Shanghai Tower. Shanghai Tower poses another interesting, another architectural design, which is a twisting shaped tower. So that poses another challenge to it. But again, we still have to deal with the shape and form, the soft soil and the twisting shape, and so on. So it's a soft soil. So we basically using ball piles to do to shape. And I don't want to go into too much on this project, but this Shanghai Tower is quite unique because it's being separated into a city within a city. It's separated into 9 zones. Each zone is about 14 to 17 floors. And basically the floor plate is on this zone is like a wedding cake, but it's only the skin outside is twisting. That's how we come up with a structural solution, not to twist the tower structure, but to twist that. And you can see the twisting form. So when you look at that, the building is twisting about 1 degree per floor, ending up to twisting 130. But this time of tapering shape of the tower and the twisting shape end up reducing the wind load and also reducing 24% wind load and 32% reduction in in structural material, and end up saving $58 million US. That's how important it is. We have the efficient shape. That this time we are using a twisting shape to be the effect, and we even use a much larger scale for that. And then, in addition to the twisting shape, we also create a notch, a notch at the outside the building to improve and to improve the vortex shedding, and improve the reduce the vortex shedding, improve the wind performance. You can see the floor plate of the building is just a series of circular floor plate. You see, the red color is the actual office space or the hotel space at the top of the tower. So, and each one is a bigger diameter floor plate. It is just the skin itself. It is twisting and twisting and twisting, rotating 1 degree. And we are hanging all this skin as a shell from each mechanical floor. Okay, so and all this, and then this is like a tube shell outside, and then we're putting horizontal pipes to transfer the wind load back to the concrete floor inside. And you can see this is all the hanging curtain wall. So you can see the hanging curtain wall, the skin is the double skin, which is very energy efficient. And this is the inside circular floor plate. And the wind load is passing through the bicycle spoke structure to the back. And they're all hanged by hanging rod all the way down from the mechanical floor. Every 14th to 15th floor. Pingan is another one. Also deal with another super high rise. It was designed at 660 meters with a tower spire. Okay, but due to the aviation local airport radar problem, we reduced the height to 599, and they cannot build a 60-meter tall tower spire at the end. But again, we also have to deal with the aerodynamic shapes, and then how we develop a structural system. So, and on this job, we end up using also a mega frame. You can see the two super column, and also the mega frame girder, on this side, and also using the super diagonal on this side of the building for lateral stability. So this mega frame, the reason I keep on talking about mega frame, why we need mega frame? Because in China, they don't allow just using the shear wall core alone or the outrigger system to be the single lateral stability system for the building. They need a dual system in order as a safety, a dual system. So and then this dual system have also have enough stiffness and strength to reduce at least 10% stiffness and not only strength to resist earthquake loading during severe earthquake. So we have to make sure that the building are very safe during earthquake. So and also with all the high wind load and everything, the mega frame also give us the ductility, the mega frame working with the two super column and give you a lot of gravity load to counterbalance the uplift, and also satisfy the building code. Okay, so even on this job, we even push out the column. We even push out the column, the super column on this side in order to reduce the vortex effect, the vortex shedding effect, in addition to the corner columns. And you can see we are doing a lot of corner shape in order to to deal with the aerodynamic performance. And but don't be surprised, the architect are very good to use all this aerodynamic design and incorporate it into the design to give a very good characters to that architectural design, and also works hand in hand with the structural efficient design. So you can see the exterior mega frame working with the super diagonal exterior truss before. Okay, so this is the construction, and also the architect are using this exterior diagonal as an expression architecturally to give more high-tech experience. So it's one stone killing two birds. Okay. Wuhan Greenland is another way with agency architect. The building was designed for 636 meters, but the Chinese government do not want to have a tall tower more than 500 meters. They encourage the developer to lower the height. So they settled the tower design with a 475 meters. So we're also dealing with the shape and form of the building, which is a character for high-rise building. And again, we have a lot of curved surface. Anytime we have curved surface and round surface, it will easily create vortex shedding. So we have to be careful. On this one, we have a tower core, which goes hand in hand with the shape of the building that function with that. And also we have the super column again and then we have the bell truss every 10 floors to work with the super column as a mega frame and the outrigger in blue color in order to give you the full stability using the full width of the building for lateral stability. Because if you use the core itself, it's not strong enough. The core is too flexible. But if you use the full width of the building, it's much stronger. Now this is the core. See how we tie the core with the exterior building and the super column to maximize structural stability and efficiency. So we get a super column, outrigger truss, and the bell truss. So the bell truss work as a part of the mega frame as well. we know has been done extensively on all the super high-rise tower design. So, and on this job, we created a lot of strategy working with architects and wind tunnel lab, RWDI. On this, we created wind slot and working with architect Adrian Smith architect. So we tapered the tower, we round the corners of the tower, we changed the, we modify the curvature and try to have slotted floor for the wind to go through just to deal with the vortex shed. So this is the construction. Now, this is tonight's main topic. I think every one of you have enough warm up on the characters of high-rise building. It's not just a high-rise building itself. We have to deal with stability. We have to deal with wind load. We have to deal with earthquake load. We have to deal with foundation issues. And well, we have to deal with the architectural design requirements. And we have to deal with the local material. We have to deal with the local material availability, the cost of construction, and the speed of construction, all the other factors. And the China code requirements or the local building code requirement, everything has to balance with each other. So that's why I have a warm-up discussion for the last half hour talking about all these issues, and they all go in hand. When it comes to Wuhan, Greenland, the architect is Adrian Smith in Chicago, and he and his team come up with a very iconic design. It is a design competition. When you look at it, everyone will say, wow, so iconic. Everyone will take a seat back. How do we do it structurally? How do I put my mega frame? How do I put my super column? How do I put my belt truss? How do I put my super diagonal outside? I have no space to do that. So it leads us into another creative and innovative design that has to work together. The thing I see that Adrian Smith architect have done is the architecture. He created a multi-facet surface on the entire tower. One thing is good is that the tower is tapering up, good for wind. Another good thing about the design is not structurally for us is it has a lot of rough surface due to the several hundred facet triangles on the surface. So it will help us a lot on reducing the vortex shedding effect. It helps, okay? What doesn't help is structurally, how do we make it work efficiently and without costing too much money? So all the scheme we have discussed on all the high-rise building we discussed before is not applicable to this. And the China code still comes in. We need a dual system. We need a dual system in the perimeter for this building. So we found a solution. And during this design competition, during the interview with the owner of Greenland, we proposed an exoskeleton system, which I'm going to talk about. This is the site. The site consists of the main tower, okay, 101 story, 486 meter tall, or 468 meter tall, 86 meter tall. And there are two residential towers with facet shape and a commercial podium. These two are residential tower, and the main tower itself is office, executive suites, and and high-end residential and a club and high-end restaurant club. And you can see the geometric geometry. According to the architectural design, the inspiration of the architect is this facet shape resemble the ice-capped mountains surrounding Chengdu in Sichuan province. So that is the inspiration. And the ridges and the valley, the ridges is the top of the mountain, is the sharp edge, the ridge forms the top edge of the tower, and the valley, the ridges represent the sky, and the valley represent the earth. And the owner loves it. But if you look at all these facet angle, they are going in and out, in and out, in and out for the entire height of the building. We cannot even put any column in the perimeter straight downward or vertical downward or sloping downward, because if we do that, most of this perimeter column will end up being pushed very way back into the floor space. If you put so much floor in the floor space, there's no more efficiency for you to use the office space. So we end up using a column which is zigzag, zigzag along the entire head of the building to follow all the facet triangle. And then if I use all this red color column zigzagging down, where is my secondary frame? So I end up introducing a brace, diagonal bracing, connecting all these zigzag columns all the way along the tower. Some of this yellow color bracing, okay, sometimes some of them span 15 floors, some of them span 5 floors. It depends as it goes up to the top. So that is how it's driving us into our design, an efficient design to make good use of what is given to us. It is a very good aerodynamic shape of the building. Now, and structural engineer, TT, and Dennis, and our team, and and the rest of us have to deal with the challenge. If you look at the floor plate, because of the facet thing, each floor plate is different. The floor plate comes in, they have an octagon floor plates. On some floor, depending on which side you cut into the facet, the floor plate vary in shape between octagons. Oh, how do I? Okay, between octagons and hexagon and also polygons. Together we have 32 edges. 32 edges in this building, 32 different edges as the building goes up. So basically, and we have 16 columns. We end up, in order to fit into each triangle, we end up having 16 columns on each floor. We end up having 16 columns on each floor. Before we talk about the floor above, let's talk about the foundation. Chengdu luckily has a very good soil. It's not that bad soil, I won't say very good. So we end up finding soil in about 15 to 60 we end up having a mudstone bedrock. We call it a shell or mudstone bedrock, around 19 meters below the 4-story basement and below the mat foundation. So we end up using a lot of caissons. We end up using more than 128 caissons for the tower. And each caisson is 1.8 diameter and bell out at the bottom to 3.7 meter diameter for bearing on the rock, on the rock. And we have a 4.5 meter thick concrete mat to support this tower. I will talk a little bit more about hand-dug caisson, which is unique in China, and it's not being used that much in the Western world. Now let's talk about the core first. The core at the low zone, okay, we are using a octagon soil, octagon core. But the thing is, as the tower taper up, the core will reduces because the tower is bigger at the base and smaller at the top. So we cannot keep the same core going all the way up. So instead of dropping this perimeter outside flange of the core, that will force this interior core to increase thickness to act as a flange, because we don't want to increase the thickness of this. We end up sloping the core in order to reduce the core and maintain a very thin web wall core. Okay, that saves us almost 700 tons of steel. Okay, 700 tons of reinforcement by doing so. And we taper the core with the core from 28 meter by 28 meter to 24 meter to 24 meter, from 50 floor to 60 floor, because we have to slope the core gradually over 10 floors in order for the stress to, it's easier for construction and also accommodate the forces requirement, the lateral forces requirement. So this is the first in China that the contractor ever construct a sloping shear wall core. And we have a lot of meetings with the local contractor, and we discussed the way how to do it, and it was successful design. This is another thing that we put into this building as part of an engineering way to make it efficient and not just do it the normal way. Now, the gravity system, again, we use a reinforced core, reinforced concrete core. This concrete core is quite easy for the local labor. Concrete material is there. But at all the boundaries, at the intersection of the shear wall, we are using wide flange steel embedded in the shear wall core in order to satisfy the strength requirement, and also cut down the congestion of rebars at all these corners. So this is quite, and then for the column, the 16 column, we are using embedded steel inside encased by concrete. But the rest of the floor is composite steel frame with concrete slab on metal deck for very fast construction. Now, going back, you can see the cross section of the building. All the columns are zigzag, zigzag. They are not straight. I don't think any one of you have seen a 101-story building with all the columns zigzag, zigzag down and never go straight. So every time they turn, they change the slope. We need a tie beam to tie them back to the floor. So because when the columns slope inward and outward, you create either inward force or outward force. So we need a beam to tie back the forces to keep it stable. Again, the core itself is not strong enough to take all the lateral load. So we're still using the width of the building for the lateral stability. So we have using 3 outrigger trusses at 3 locations where the mechanical rooms are located. The mechanical rooms are located to make our structure very efficiently located and designed there. Okay. So this is the core with the concrete, and then the 16 columns. Now we have the outrigger truss at the mechanical floor at 3 levels. And then we have the perimeter truss so that it will like a rigid body. And then we have the horizontal floor diaphragm to try to balance all the forces on each. And this is the isometric view of the structural system at the outrigger truss system at 3 locations of the tower. Now this is the bell truss showing the column. Okay. So you can see the core and then the exterior column, and we are connecting the core to exterior column for the stability. So you can see how the column, the perimeter column are all steel column encased by concrete, but the diagonal bracing, okay, they are steel square tubes. They're steel square tubes. Now you can see this whole picture of the exoskeleton. Now, when this exoskeleton, since we don't have a mega frame and super column, we're using this exoskeleton which is fitting exactly the architectural serve more than 100 triangle facet facade. And they are in and out, in and out. They are coplanar. Okay, they're non-coplanar. And when we design it, they become a very efficient dual system structure, contributing to the building stiffness and also for the earthquake design requirements. And it becomes an integrated stable lateral system for the tower with this exoskeleton, which is unique itself, that goes with an architectural design with high aerodynamic performance and iconic architectural design. Okay, and also the triangular bracing maximize the stability of the structures. So it is about, okay, now we talk about the advantage of this 3D exoskeleton. At the end, we found that this exoskeleton is good in different places, contribute to almost 5 to 20% stiffness to the building, lateral shear forces. That's how effective building. But the China code requires the perimeter frame to take a minimum of 5 to 8 of the total base shear at the minimum, sometimes 10%. Okay, so we more than satisfy the China code and also satisfy the architectural requirement with this 3D exoskeleton system in the outside. So you can see the perimeter moment exoskeleton also take about 60% of the overturning moment at the base. This is how efficient it is. And meanwhile, it gives us a secondary lateral system. So it is difficult at the beginning to try that, to think about this idea, but it never stopped us and our engineers to think out of the box, to try something new for a new building design with the architect. So our creativity continue, and this is encouraged by our Thornton Tomasetti culture as well. So not only that, the curtain wall is multifaceted, so we have to put a lot of mullions, a backup structure for the facet, for the facet facade curtain wall. So this exoskeleton also become a natural mullions backup structure for the facade as well. So the structure is exposed to emphasize the architectural language, which is one stone killing many birds. And of course, connection design with all the members connected together between composite, steel and concrete structure column and the steel beam and the diagonal beams are very complicated, which we're going to discuss in other time. Now, I'm talking about performance-based design. For all our buildings in earthquake zone, we always perform, and especially in China, they require us to provide performance-based design, especially for severe earthquake seismic, to make sure that the building is safe. The reason, okay, the reason the advantage of a performance-based design are numerous, okay? Because let me get some, okay. Performance-based design is so important because we cannot just use the code-based prescribed linear design method. Performance-based design using nonlinear dynamic and seismic analysis will give us the actual behavior of the member, the overall behavior of the whole building structure due to its dynamic behaviors. And also, we can consider the nonlinearity and the ductility of all the structural members in the lateral system that the code-prescribed linear analysis cannot do. It gives us a better building design and more accurate building design and performance. So, I always recommend doing performance-based design on our high-rise building, especially in seismic zone. So for seismic performance-based design, we usually choose about seven seismic curves, and four of them are the 7 time history acceleration curves. 4 of them are the actual earthquake time history curve, and 3 of them are synthetic, and we have to scale them back to scale these curves back to the local site geotechnical condition for suitability to use on each site. So performance-based design will make sure that the core will remain largely elastic under compression, and the link beam is going to yield during severe earthquake to dissipate energy. Building have different dynamic properties, and you have a building period. And for this Chengdu build, since this is a symmetrical tower, the first mode is about 8.8 seconds. The second mode is also 8.2 seconds. The torsional mode is about 4.9 seconds, which is very ideal and very efficient. So this building is not too stiff and it's not too flexible, and we don't need a 2-mass damper. So building deflection, we just make the China code requirements, and also the acceleration requirement is about 7.5 mg only, which is very low. So this is some of the site pictures. Excavation for 4 basement. You can see it's a deep. They do the open lot excavation with cross lot bracing, and all these are temporary site structures. And this is a hand dug caisson, 120 something of them, and each one has an umbrella to shade around the sun. They are not using in China on this specific product. They are not using boring machine. They're using a very light hand tools to dig 15 to 19 meters into the soil until they reach the shell and the mudstone rock, and then they bail out. So, and of course, as they go up, they have liners to protect the workers. So actually, it's still very dangerous when you are 15 meters, which is about 40, 50 feet below grade or 60 feet below the ground. And still a very unique kind of, I think it's to the Western world, it's very risky. It's called hand dug caisson. And this is most of the concrete construction that the local contractor are very good at, and the concrete column with embedded steel. And also you can see the diagonal exoskeleton square steel tubes. So the construction continued to go on because it was slowed by the pandemic. And I think they are resuming full speed with the construction. Now, I just want to make sure that we have more time to talk about performance-based design. And first of all, you can see the slide further on. The performance-based design is a very important parameters for us to start setting the goal when we design the building, and we have to discuss with the owner what is their performance goal for their building, and then the engineer can go for that. But life safety is the bare minimum to make sure during severe earthquake, life safety is still maintained, and then we will not collapse. So I think that I just want to share with you. How come it's not okay? So why I just mentioned before why we do performance design, because the code-based approach does not address it innovative and the different kind of structural system, but just like this exoskeleton and some of the special structures, special shapes, and a lot of code cannot be applied directly with linear analysis or with innovative and structural system, and also a lot of structural system exceed the code limit, and also we really enhance the building performance under structure. So basically, we want to design our building for severe earthquake, which is a rare earthquake for life safety. And I don't think for moderate earthquake, our goal is to have immediate occupancy with some minor fix, and frequent earthquake with some operation. So this is something I want to share with the audience here who want to understand the challenges of seismic design and wind design and what engineers can do about it. We can overcome these challenges safely. Okay. Now damping again, people on the high-rise building, when the wind blows, building will have motion sickness. Because building will move, and it's not the building movement; it is acceleration of the building that give you the perception. Just like when the airplane is decelerating or accelerating in the sky, you will feel it. Okay, that is the acceleration or deceleration that give you the motion perception. Same thing for the tower. If the building is accelerating too much, something like, I would say, anything more than 25 mg or from 20 mg up, you will feel the perception. So we have two mass damper. We have two mass damper. It's a pendulum that will activated by the wind. And then when the building sway this way, it will counter the pendulum that weighs several hundred tons of steel will swing to the other the opposite direction as a damper. Okay. And sometimes we use water tank. We fill with water as a sloshing. So the water inside the tank is sloshing to provide damping effect. And then office sometimes also develop a hummingbird kinetic system, which have a lot of water pipes with control valve, and we can hang it. We can put it on the perimeter. We don't need the heavy water tanks, and it's very flexible. There's another damping system with water inside control. That's another new technology that our Thornton Tomasetti and Motioneering developed together. Now for earthquake, we have the viscous damper, look like a shock absorber with a fluid inside the dampers to absorb earthquakes, following like a shock absorber, and this is that will provide some damping. And the other one is a viscous damper, and viscous damper we have some elastomeric, some rubberish type of material inside, viscoelastic material to absorb energy. And then the other one is the base isolation dampers at the base of the tower. You have a base isolator at the base of the tower to as a damper. Okay. And also we have coupling damper that we connect two shear wall together. You have a shear wall, there's a link beam, it's the coupling damper. And sometimes we can use damper between the outrigger and the column, and then with a viscoelastic material inside. So dampers is another good tools mechanism for us to handle seismic and also wind acceleration as well. So there's another viscous damper wall and yielding damper. Now I want to show you a video, a short video that show you the model on the left is with damper, and then the model on the right is without damper. You can see the effect, and when the damper is provided to the left side of the building. So we are giving an earthquake effect to the building, and you can see the building with dampers on the left is not moving that much, and the other one without dampers, even with the same structure, is moving a lot. So we have to design on the right building without damper with a lot more construction materials and stiffness to handle it. So damper also save a lot of construction material and the structural system. So I cover a lot of materials tonight. It may be a little bit quick, and I hope it doesn't bore all of you. But if you have any question, you can address to me later on. It's a good evening. Everyone wants to go out to have a drink. I don't want to hold you up. I'd like to thank Carol and Dan and the New York Skyscraper Museum for inviting me to share my experience, our Thornton Tomasetti experience, and my team experience with you all. And I also thank my colleagues who work with me on all these projects. It's not a one-man show. It's a whole team show. It's always a team effort working with everybody, with the architects and everybody and my colleagues. Thank you, everybody. Okay, good night.
Thank you, Dennis, and don't go away yet, because we'll just take a few more minutes, and then maybe one or two questions from me. And you certainly have shown us everything. So there's practically no stone or foundation unturned in your presentation, and the list of all of the considerations that you mentioned. So I really appreciate being able to cover Petronas Towers and all of these chapters in different approaches to working over 2 and now almost 3 decades of pioneering Supertalls in Asia. I think it's so interesting that you worked on Petronas on the team, and we'll talk more about it from the perspective of architecture in a couple of weeks. And now with these other projects, you've led the team. So you make the point, the excellent point, that engineers have teams, all kinds of engineers, including MEP, which we really haven't covered in this series, but structural engineers constitute a very large team, of part of the even broader universe of the team of architecture and other kinds of consultants, curtain wall consultants and everything else. I really did want you to talk about Chengdu in this series, because it's such an astonishing building. It's kind of hard to imagine how it moves in and out. And you described that for us. So I hope I understand it myself a little bit better. I have maybe 2 questions. One actually relates to something that Mark Sarkisian talked about in his lecture last week about Jinmao, and then bringing that model into the 21st century and experiments in innovations in engineering solutions. When he talked about membranes, structure as membrane, and you're talking about exoskeleton, sounds a little bit like a biological analogy, certainly. And I wonder, where, if you think of the inspiration for these designs, or where do you get the inspiration for the design, which you've described very much as problem solving? Is that the case, or is there a theoretical dimension that you bring to the analysis that is balancing what you've described as a kind of practical problem solving in your talk?
Well, for each project, I'm sure it comes with a lot of design experience, because over the years, we gain a lot of experience, or also painful lessons. Some of them are good, some of them are bad. We learn from different lessons what is good to use, what is not appropriate to use, what we try to stay away. There is no one single formula for us as a structural engineer to prescribe as a special only solution for a building. We always tell ourselves, how do we do it better? How do we do it better than our last project or other projects, given a shape? Even that's why we have competition among our colleagues, even among other firms. One firm will think of it to do it this way, but we try to challenge ourselves. How do we do it better? Whether you call the exterior as a membrane, membrane is like a layer of structure, and then I call it exoskeleton, which is another layer of structure. What layer of structure can be done? Even for the Chengdu project, someone may say, I will do a super diagonal, a big diagonal in a different way, and try to talk to the architect, and I push the diagonal in the middle of your meeting rooms, in your conference room. But we don't want to do it. We continue to challenge ourselves. Don't forget that we are still working for the architect. We have to make sure the architectural design is being followed and executed. So, but at the same time, we have the responsibility for the construction cost, the structural efficiency, and the structural safety. So it is a back and forth exercise. And I emphasize so much is, if we care about the project, we have to go extra miles. On this project, Chengdu project, this is not the only scheme I study. I also study other schemes with the shear wall and other system. Okay, can we do some other way? But internally, we do alternative scheme 1, 2, and 3, and 4 before we present what is best. I'm the one who went to the presentation with Adrian Smith in front of the owner in the design competition. If we lose this job, I cannot get my plane ticket back to USA. So I had to make sure I win and make sure I present all the good facts of our design, how efficient it is in front of the owner to beat the design competition, to win the design competition. So everybody was, wow, when they look at Adrian Smith multifaceted building, they say, oh, who's going to build it? It must be very difficult. Until I show him the exoskeleton, everything is so repetitive, it's so simple. They ease their fear of building it. It's so simple. I give them a solution that give them their dream tower. So they win the project and we have a job. Otherwise, I don't have a job. So I encourage everybody, when you see an architectural drawing, architectural design, just take a deep breath and think about it overnight and draw more sketches and sketches. I'm still an old-fashioned man. I draw sketches. And I ask everybody around me, my colleagues, okay, everybody around me for their input, and I digest them and put it together with mine, and it just put it together. It's my same thing. I sometimes I ask you, I say, Carol, what do you think about it? It sucks. Okay, let me go back to work. So I think that makes our design life very interesting. And it carries that. This is my 43 years at Thornton Tomasetti. I never get bored on any job. Okay, I still do hand calculations by hand, according to Charlie Thornton. Charlie Thornton told me, Dennis, do it by hand is faster than computer, better computer, within 10%.
Well, Dennis, I've known you for a long time, and I've listened to many lectures that you've given in other forums, CTBUH and others, on either in person or on video. And like all structural engineers, I think, and I say this as praise to all of the people who have presented in the series, you explain things extremely clearly. You emphasize simplicity as part of the solution to any structural problem, and also of buildability. I saw in the participants that Ahmed Abdel-Razak has joined us a little bit late. He's going to be speaking next week, and he will talk about solving those problems of constructability, as well as advancing the knowledge of the industry for unprecedented buildings like these Supertalls by monitoring systems. So understanding construction is absolutely, as you explain, part of the problem of the structural engineer. So clarity of structure, simplicity, exploiting gravity, all of the things that you explained. And there's one thing I just would, to conclude, I'd like to you to emphasize a little bit more in this context, because I've heard you talk about it so convincingly in so many different instances. And that is the constraints of the code in China, especially. You mentioned the dual systems that are required. And then I have heard you talk about how you pressed Chinese authorities in order to accept some solutions, which were clearly more efficient and more economical and better structurally. So I wonder if you could talk a little bit about what you described as kind of the local conditions, as well as this kind of international context of the international Supertall, international experts that come, but then are constrained or guided or channeled by the local conditions, whether it's choice of steel versus concrete, the codes that need to be accommodated.
Yeah, good question, Carol. I started working in China since 1992, and when there's no super high-rise building there. So my first project in China is the Plaza 66 on Nanjing Silu, the 270-meter tall, tallest concrete building in Shanghai with KPF architects. So when I start working on that, I have to use the Chinese building code. At that time, that code is not designed, was pretty much based on many Russian engineering influence. So the building allowable deflections and all the formulas and everything are quite different from our American code or international code or Boca code at that time. However, we do have many smart and great and good engineers in China. They're very good. They know their situation. That's why they're working with us together to see what we can do to address about the code. However, when we address this situation to them, like all the constraints and the limits and the stress limit, the factors of safety and so on, deflection limit, all the factors in the code, we have to approach them with due respect because this is still a government authority. So I start taking a very respectful and professional dialogue with them, step by step, each project by each project, proving to them that if I use these American guidelines, American code or international code, it will still work. And through analysis and design to show to them, so they keep on accepting it. And in the expert meeting, all our jobs are going through expert approval and review. We discuss it, and some of their feedback is good. Not everything in American code or whatever is good. And we also listen to them, and we end up to have the best of both worlds. Really the best. The building I have just talked about and the one that we design and other design buildings are very safe, especially for super high rise. But their building code originally was intended for different calibers of users in the village, in a small town, in a small city. So when you have a big city with all this complicated structure, the code, certain part of the code become obsolete. They did not address everything. So that's how we come in working with them. And the Chinese engineers are extremely professional and good. They're very smart, I'm telling you. They're smarter than me, they're better than me, I can tell you. I still learn from them. So we have a win-win situation. It's a good collaboration, but you have to know how to work with them so we have a great dialogue. So far, I'm very happy. They become my friends, my professors, my teacher, or whatever they call each other. They're very respectful. One thing about working with the Chinese engineers and professionals, they're very respectful. And I think we end up to have a very happy result for the project and for society. Just like one thing, over the world in China, they have refuge floor for fire. Right now, the refuge floor is every 15 stories before, 20 years ago. Now they reduce it to every 10 floors. You have a refuge floor for people's safety. In America, in many countries, we don't have it. So how come our American code did not address it? How do we do the firefighting, right? So, and then once they address this, there are many things they suggest are very good, are people-oriented and safety-oriented.
So this seems like a perfect way to conclude the evening as technology begins to strain, and to thank you so much for giving us a truly worldview of designing Supertall. So Dennis, you've overwhelmed us with your knowledge and your experience. So thank you so much. And we're going to ask everybody to join us next week when Ahmed Abdul Razak is going to talk about Europe's tallest building in the Lacta Center in St. Petersburg. We hope to bring you back all into a discussion to try to grasp what we've been learning over this 12 weeks.
Well, thank you, everybody. And even all the buildings I just showed you tonight, and our company, Thornton Tomasetti, are still currently designing 5 super tall towers in our desk. And I'm working on these 5 super towers. So the development and the design construction on super tall tower still ongoing and very active. So we have a lot of area to continue to work with Carol Willis and make her museum very busy, okay?
Onward and upward, as I always conclude my emails.
I always think construction is better than destruction, so we're in the right business.
That's great. Think positive.
Yeah.
Thank you, Dennis. See you next time, everybody.
Thank you all. Thank you all. Thank you. Thank you.
Hello, welcome everybody. Welcome to the 11th in the talks of Worldview Designing Global Supertalls. The 11th of what will now be 13 talks, because we've just added a bonus talk at the end on Petronas Towers. And as a matter of fact, our speaker tonight, Dennis Poon, was an engineer on the Petronas Towers project in the mid to late 1990s. So he'll be able to give us an introduction and frame the kind of evolution from the first Asian supertalls to a project that he's is working on, that, or has worked on, that is now under construction, the Chengdu Greenland Tower, which has, as you can see from this slide of the introduction and the page from our website, a non-coplanar exoskeleton. Now, this is such a fascinating concept, perhaps a bit esoteric maybe in not in engineering parlance, but in architectural understanding. And it's a building that I wanted to be sure that we would be able to cover, because it's one of the featured buildings in our exhibition, Supertall 2020. Soon we hope to open, as the Skyscraper Museum's gallery is projected to be able to be open to the public, we hope sometime in June. So let me very quickly go through some slides that predict our upcoming lectures, and to also give you a little bit of an introduction to the career of Dennis Poon, as well as the subject for tonight. So as you know, the second part of our series on designing global supertalls is focused on engineering. And we began with Bill Baker and a whole lineup of structural engineers who, like our colleague, the late Les Robertson, to whom this series is dedicated, were the team leaders in the design of some of the world's tallest buildings, and among all of the buildings that we call supertalls at the Skyscraper Museum, that is as tall or taller than the Empire State Building, 380 meters or taller. And indeed, these towers go up to over 800 meters, with the Burj Khalifa, as Bill Baker and others in the series have described. But we dedicate this series to Les Robertson, and we think of him through all of this time in the months after he passed away back in February. The towers that are featured in our exhibition, and indeed in the lecture series, are on the page of the website, and you can see him here in a lineup at the bottom of this screen. The second one from the right, is the Chengdu Tower, which is the subject of Dennis's, or actually the culmination of Dennis's talk, because he's going to lead us through the history of buildings that he has worked on with Thornton Tomasetti, his firm, where he is the vice chairman, over a career that has now spanned about 3 decades. And the last of the foci of our lecture series and the featured buildings in the exhibition is the Lakhdar Center, a building that's not that well known, and which will be described by Ahmed Abdelrazak in next week's lecture from the perspective of constructing supertalls. So this is the page from our website that promotes and details its lecture. I wanted to mention too that Fred Clark of Pelly Clark Pelly, who founded their firm with Caesar Pelly as the founding partner, and now Raphael Pelly, Caesar's son, is also the co-partner in Pelly Clark Pelly. And as the architects for the Petronas Towers, the first of the world's tallest towers not to be anymore in North America, we will fill in that early history as a kind of coda to the series. So Dennis's designs can be seen here in the center of a snapshot from our website in the Petronas Towers, as well as in Taipei 101, and he will talk about both of these buildings. He will also give us a bit of background on the Shanghai Tower, which you see here, and Pingan, two Chinese towers. They're blue here because the blue buildings are in China. And Dennis leads the Thornton Tomasetti, the TT offices in China, in Beijing and Shanghai, also in Hong Kong, and I believe in Ho Chi Minh City. So his beat is really Asia, and he is going to share his long experience and insights in working on Asian supertalls. So with that, I think I'll invite Dennis to turn his camera on and to come onto the screen. And I think I've given him sufficient introduction with his august title of Vice Chairman of Thornton Tomasetti. Here is Dennis Poon. I will now stop my share. Dennis will come on the screen and begin his historical view of both his career and the Asian supertall, because his career coincides and intersects with these key buildings. So Dennis, please take over.